Ashutosh Kumar Jha. Presently, he is serving as a scientist engineer at the Department of Geoinformatics in Indian Institute of Remote Sensing. He holds MTech in Remote Sensing and Bachelor of Engineering in Computer Sciences. He has the expertise in the field of geospatial modeling and processing optimization of raster vector data using high performance distributed computing. Currently, he is working on big data, machine learning, and 3D modeling. He has been actively involved in weather forecast and air quality application development. He has built an open source land use land cover dynamics modeling framework called OpenLDM. He has been awarded Best Innovation Award in ACRS 2017 for the development of mobile application for the municipals. Today, he is going to talk to us about the GIS data modeling, map projection concepts, and the introduction of spatial analysis in GIS platform. We welcome you, sir. Uh,
Thank you.
and now you may proceed with your presentation, sir.
Talking about the GIS data models, so it's very introductory lectures where we just talk about the different kind of data models which can be used, especially the GIS data models. I think the conceptual model already is being covered, so we'll just see what are the different logical models are there, and then how those models is being used for different GIS analysis. So that's what we'll be looking at. Then we'll see a few ways to store those models, like a few important formats which is being used in nowadays, including open source and closed source environment. Then we'll also see a few examples of spatial analysis. Spatial analysis itself is a quite big topic, but we'll just scratch the surfaces and we'll try to understand what are the different potential of it. And we'll also see the upcoming technologies where 3D GIS analysis methods are there and how the location-based services, especially the augmented reality and web-based augmented realities, how those are being used and different applications can be built. So we'll see those potential as well in next 1 hour and 15 minutes. So just to bring back the requirement of GIS usage, which is actually the most important aspect. So any analysis or spatial analysis has to be driven by based on few requirements. And since on the GIS domain, we are having different places and different requirements, so accordingly, we have a lot of different diverse way of implementing different things. So let's take an example of finding out a location. So that's location A and location B, and you need to find out the distance between these two places. So to solve this problem, there are multiple ways of doing this. One is the shortest distance path you can compute. Another one is the shortest time path you can compute. Third one is the smallest number of resistance which is possible that can be computed. So there are a lot of GIS-based question is required to be solved under this requirement. So to solve that, we have a very complex realities where we see a lot of different road networks. So generally, we do a simplification of those models. And since in this case, our requirement is only to finding the path, so we are only interested in basically the networks. And based on that, we get few answers. So this is basically the normal flow of any GIS requirements. And these requirements generally links to the different kind of projects, especially it may be ecological, cultural, connections and so on. All of those different GIS applications, you'll be having a few set of user requirements. And based on those user requirements, you are going to construct a few simplified models. And those models will be used for generating the GIS questions. So generally, in any one of those requirements, we'll be having 4 different components, and those are actually linked. So basically, you are having a data, then corresponding environment in which the services or application will run, the kind of functionalities, and finally, after executing all these, you want to result back to the users, so end users. So generally, the data, you have to have a proper organizations of those data sets, services, set of services, and then finally you carry out few spatial analysis. So few spatial analysis tools are like geometrical based tools, there are statistical based tools. Now there's also a modeling based tools are also there, which works on a data stream kind of environment. And then finally you do a visualization of those components. So any one of these GIS uses, there's another important aspect which is called a model analysis and modeling process, where there is a kind of iterative approach is being followed, where based on the user requirement or data set, you carry out a model analysis like sensitivity, calibration, verification, and validation steps. And if you're happy with the outcome, then you use it in real environment, the applications. Or if you're not happy with the results, then you go again back to the development of different conceptual and mathematical model and you do it. So this is basically the different applications or requirements in GIS uses. Now you'll see that how these uses are actually linked to a different GIS data structures. So coming back to finding out the distances between two locations at A and B, we need to find a path. So this is basically a very simple requirement where two location has been given, and our objective is just to find the path between place A to B. So in this case, we are assuming that we are interested only in the shortest path distance. To solve this, basically, we have to do some kind of those GIS questions, that how we can find out the path based on these simplified models, where you may be having a multiple path, so how we can give and estimate which particular path is appropriate or not. So those are the GIS questions. And these GIS questions, again, we ask, basically gets converted into what kind of data we have and what kind of analysis we want. So do we want the users to provide a kind of interactive analysis, like where he can change a few parameters, or he is just going to give a requirement and you are going to give the output. So that's basically the GIS data processes through which this GIS analysis is being carried out. And finally, answers is we get the answers. So this is basically, in this case, GIS works as a machine interfaces where a set of questions which is related to different human applications gets the question is being given, and you give a questions back to machines or the systems, and finally you get an answer. So that's the basic job of GIS analysis. So let's take an example of this, basically the problem in hand. So generally, what are the informations which is available to us? So we will say that we are having a set of data points, that is a tuple A and B, and we know its name and corresponding locations. And there are few connections which is existing, an important point, which generally in basically in daily terms or in normal terms we say landmarks. So there are a few landmarks, road or junctions might be there. So these are the information which will be available to anyone. So if you want to ask a person in local to, let's say in Dehradun, then he will just tell all these, he is having this information, and based on that, he will give you answers that you can go from A to B by taking first a road called Kalidas, then you take a New Kent road, and finally, with the help of Rajpur road, you can reach in 8 to 20 minutes. So this is basically, if you ask anyone, so that person is going to give you the answer in this solution in this way, in a way to based on the human languages. Not just try to convert or provide these informations back into a machine-based system, because the GIS systems is actually a systems where we want to build and machine-based systems where answers can be given immediately based on the information available. So whatever earlier information we had, we just trying to define some of the structures or the basic definitions, and based on those definitions, we are going to map to the machine-based data structures, and finally we'll be getting the answer. So let's say in the point A and B, or location A and B is being given as an point geometry, which will have an associated coordinate systems, and it is have some kind of attribute which is called the name of those locations, and then there are a lot of line segment in between. So those line segment is having different names like New Kent Road, Rajpur Road, and so on. And these line segments again have a few attributes like what is the time generally is being taken if somebody is traveling from one segment, one location at one end to the another end of a segment. So based on these data set, then a simple set of algorithms can be carried out, which can provide a overall output in terms of total time taken by the for covering that route. So now just see that how this data set is getting organized. So at the conceptual levels, we say there's something, two part of your data sets. One is called geometry, another one is called attribute. So again, geometry is widely broken down into point, line, and then polygons. So polygons is nothing but a closed line. So basically on the data structure level, these two are the two main component of at the geometrical levels, that is point and line. And then you're having a few attribute data set, like we are having a place name and the corresponding segment names and the travel names and so on. So those are called the attribute informations. So once you break down these two important aspect of any geospatial data, then we can add some additional informations. Those are called coordinates, reference systems, and the scale. So based on that, what we can do, we can create GIS databases, which is nothing but a set of maps and corresponding attribute informations. And these attribute and map informations can be a separate vector raster or 3 data set like TIM, or it can also be stored directly in the different kind of relational databases like PostGIS and so on. And these map data or geometrical data are links to your attribute data. So this is how we create a normal GIS data sets. So in your GIS data set, you expect to have locations, basically the reference points. There will be a few attributes and set of auxiliary information. So combinations of these two is going to give you an appropriate data structures which can be used for GIS analysis. So if you see in major GIS world, you deal with two different ways of representing your data set. One is called vector and raster. So vector is nothing but a set of geometrical based objects. So this is basically, I'm talking about the geometrical properties. In case of vector data, you'll be having a geometrical properties where different point locations will be given, and point as an individually it can be a points, or if a point gets connected, then it becomes a multiple line segment, and if it is a closed line, then we call it an area. So these are the three different I should say geometrical sub-classifications for which is present in GIS domain, that's on the vector data. Where apart from the vector data, we are also having a raster data sets, which is nothing but a kind of grid-based systems where the points are being provided in terms of taking the positions at a particular location. So you are having a locations. The difference between these vector and raster data set is that in the vector data set, generally you'll be having an attribute attached to a point. So this location will be, it may be a fractional one, where in case of raster, we say that one particular group, whole grid is being taken by that point. So if your grid resolution is, let's say 250 meter by 250 meter resolutions, then even if point is will be represented by 250 by 250 small segment of that part. So that's the basic major differences of that. And due to that, you see the impact. So in the case of vector, you have a very smooth geometry, where in case of raster data set, if your resolution is coarser, then you'll be having a kind of staircase effect that is quite visible in it. So these are basically two ways of representing the systems. And all these raster or vector data sets is governed by a set of coordinate reference systems that is basically giving the position with respect to origin. And then these reference systems are being given with respect to a local references, because over here we are talking about 2D analysis. So it means like all the data set we expect it to be in 2D projected system. So there you need to have some kind of local reference plane. And on this local reference plane, you just do a kind of projections of all these locations. And that's how we create an auxiliary data sets, which in combination of these geometrical locations, you get a complete data structures. Apart from these two raster and vector data sets, there are also a TIN model. It's a kind of point data set or kind of vector kind of format, but it allows you to have a 3D informations, and there are few runtime application of is being carried out on those vector points, so giving you a kind of 3D outcome. So TIN is just one of the models. Apart from that, in the raster world, you have voxel based systems where resolution of the voxel will be in a kind of cube. So that's what you do it in case of raster data format. So in the earlier, we have seen that there is an systems, especially you need to do a kind of transformation of your earth-based or geographical-based systems back into a 2D plane and paper. So this is basically done with the help of projection systems. So most of the time we are seeing that we feel that our earth is a kind of spherical globe structure, but in reality it has a very odd shape. So it's this is just shown over here. So we need to have some kind of coordinate reference systems where this particular shape is going to be represented in a 2D format. So that's what we try to do. So to do that, at any places we try to create a kind of local reference plane. So those local reference plane can be in 2 dimensions. So like in this case, this is basically an orthograph. Any question?
अब आ रहा है. क्या हो गया था?
कुछ नहीं हुआ था, डिस्कनेक्ट हो गया था.
Any question?
अभी भी आ रहा है. अब जा रहा हूँ. अगर नहीं है.
Any question is there?
No, sir, you continue.
Okay, so
चलो चल जाएगा आधा घंटा. ठीक.
I think Sonkar is having mic on, so I think some noise is coming. So anyway, so coming back to the projection systems, so you're having a local reference plane that may be one of way of representing your projected system, that 3D world, or we can have a kind of average surface fitting for a particular area. So based on that, we have multiple families of projection systems. Like you're having an geoid, basically the shape of the Earth, which gets approximated into either in a spherical coordinate systems. So you create a spheroid, or you create different shape of a spheroid can be created based on the accuracy or the local accuracy which we want to find it out. And finally, you create multiple surfaces. So these surfaces can be a cylindrical one, or it can be conical one. or azimuthal one. So based on that, you do a projection of all those systems, which can be first your irregular shape gets approximated by a simple shape spheroid. Then these spheroid is basically a project which can be used as a surface, and finally you open it, this surface into a 2D or flattening you do it, and that's how you get a projected system. But in the GIS, we do not have to worry about these projection system much. Just basically the reason for that is this is being done, or it's been well defined, and based on our requirement or accuracies, we can select any one of the projection systems. Most of the time, what we have to deal with is that what kind of property which we want to preserve in our projection systems. Like, do we want to have a angular direction we need to preserve, especially in case of navigations. This is the most important properties. So it means like wherever the north direction is there, that north direction should always point to in upward directions, and the east direction has to be at the 90 degrees. So it means like there may not be any kind of distortion between those places or those latitude and longitude. So this is basically an angular conformity is being expected in map, like one of the property which is required. So to preserve this, we have Mercator or LCC based projection systems, which makes sure that the angular conformity is being maintained, and all the important like navigation charts and other thing is being built considering the angular conformity. Then we have a distance where we can, at any scale, what we can do is we can keep distances between the 2 points which is being shown on a map is same as the distances on a real Earth. So that's basically an the equidistance projections we call it. So planetary carry equidistance or equirectangular projection system are a part of that. And then we are having a projection system where area has to be kept constant. It's like whatever area we see, that area has to be constant. So that area should exactly match whatever the area which we see on the Earth. So these three different properties will be required for different projection systems. So most of the time, what happens is that all these different projection system is going to preserve one of them, or that's what it tries to do. So at least one of them is being maintained. But there may be cases where sometimes we would like to have a kind of all the good part. So it means like we would like to have a kind of compromise on angular conformity or distances or area. So that is also possible. So based on that, you're having an Robinson projection, which is being considered to be a compromise where distances between the places is same as what you see on the map projected systems, or it also have a kind of area preserved. So it means like the shape of the objects will be the way it is. So that's basically projection system it is called. But apart from that, having angular projection systems which keeps the distances in a specific, basically the direction where the north and east direction are always 90 degrees. So it means latitude and longitude is always going to cross at 90 degrees. So this is basically an angular conformity. Then you are having an equidistances which is being put in. So equidistances around the latitude or longitude, or it may be in the azimuthal direction. So like taking the center, and based on that you start drawing it azimuthally. So you'll be having an equidistance projections along any one of those radii, or it's also possible to have at latitude longitude based equidistance systems. Then we are having an equal area cylindrical projection systems where area of all the features becomes or is being kept in a constant. So these becomes an important properties whenever we try to do some kind of analysis. So let's say if you're having a data set in equidistance properties, and if you just compute the number of pixels falling in these areas, and that if you try to compare it with the reality, then you see that there will be a differences. The reason for that is that it doesn't shapes, the shape is not being maintained, so there will be some kind of deviation which is possible. So whenever we select any kind of projection system, we should be very clear what we want to compute. Are we more interested in area or locations or distances and so on? So based on that, specific projection system is being used and it should be used. So once we define the projection systems where how the shape is getting defined, then we simply create a reference coordinate system. So we are well aware of geographical coordinate system, that is the latitude and longitude. And these latitude longitudes defines the places, and based on that we can create a GCS coordinate system. So any one of your basically the GIS dataset or GIS dataset is going to have the location informations in a tabular format along with the coordinate systems. In the coordinate system, it will define which kind of geoid or system is being used for approximation of the Earth. Along with that, the latitude, longitude, location or extent will be stored. So this is just one way of representing it, where latitude and longitude you are storing it in your data set. There are also called projected systems, which is nothing but taking this GCS system back into projected plane, and that projected plane is being used. So UTM basically is the most widely used projection system, especially with the availability of GPS-based systems. Now most of the people wants to find out our positions, which is being given in basically with reference to UTM projection system. So over here we will be having a UTM-based projection system and widely used in GIS. Mostly this accuracy of this is being considered to be minus basically the 85 degree north to 85 degree south. In these regions, it is being considered to be most appropriate or suitable to be used. So at the poles, the UTM system should not be used. The different azimuthal systems should be used for proper finding. So all those projection systems and coordinate system, when you define, then you simply store the locations. So this is basically a kind of tabular data structure which is being stored in a file. So we'll see what are the different files and how those getting stored. So generally you'll be having a point where each of those points will be numbered, and then their X and Y coordinate systems will be stored. So X and Y with respect to projected coordinate system is being shown in this example. So you're going to have this one, then you can create a simply line which is nothing but a set of point traversed in an order. So you'll be having a line which is having a starting point and ending point, and in between you have to traverse from point number 1, 2, 3, 4 in a straight line, or at the minimum distance. That's the basically.
Sir, I'm really sorry to disturb you.
Any
sir,
question?
Do you change this? Yes, sir. Yes, sir. So, do you change the slide, sir? Because I cannot see the different slide. I'm still looking at the first slide what you have shown, sir.
Is it the case with everyone, or this is the specific case of yours?
I do not know, sir, because
Yes. Okay, so I'm on that slide.
Okay. Sorry, sir. I will check it.
Okay, so there may be issue with the few. I mean, like your probably you need to reset your visualization or maybe re-log in it.
Thank you, sir. Thank you, sir.
Okay. Then you can create a polygon. The polygon is nothing but the same. In this case, the polygon is not having a start and ending point, but rather than it's a closed loop. So in this case, we can have a point, different point lines can be combined together, and you can create a basically a line segments combined together, and that is going to give you a polygon. So this is basically a conceptual level or how the data is getting stored, and then for the basic vector data sets. So the example of those data sets or the basically a logical organization is there are a lot of different models are there. One is called spaghetti models. Quite early it is being used and is still used in especially in it has been derived on the basis of the CAD system. The CAD-based system actually uses that. So in this case, what you do, you simply take different features. Like in this case, you're having A, B, C, where A is a polygon, B is a point, and C is a line. So you just say that A is a feature which is having 6 different points. That's what you put it over here. And then you just store all the 6 coordinate system locations. That's what you are doing. So what will happen is at the beginning, you'll be having a feature and corresponding how many points that feature is consist of that you write. And then entry of all those 6 points is being shown. So till here, it represents a kind of the feature A. Similarly, in the case of feature B, which is just a single point. So feature B is just having a single point and corresponding locations. Similarly, you'll be having a feature C, which is having 4 different points, and this location is being stored. So all the different point line polygons are actually being stored in the same file, and this is quite early stage of the data models. In fact, nowadays people are also storing it in this format, especially for the very large data sets, because in the big GIS or the big geospatial world, the data structure is not yet free. So people are trying to use a flat file based systems where they create or partition the system on the early stages. But in traditional GIS software, which has matured now, is not going to store the information in this format. The reason for that is the cases is that there will be a lot of repetitions and so on, and that may be causing a lot of duplications in your data sets, and as well as there is no topological relationship. So topological relationship is telling that which of the portion is on the left and right side. So if you're having a feature, so let's say this line C is a feature, and if you want to tell what are the features which is available on the left side of this line or the right side of this line. So for that, you have to know or store the informations that along which line or direction the feature is being stored. So those are basically a topological relationship is required. In few of the GIS analysis, topology is must. But in case of spaghetti model, there's no topology is being built in. And since all the files are same, so there will be a kind of repetition. For example, if you have this polygon around, and you also want to create another features called D, which is nothing but representing a perimeter, then in that case, what will happen is the information for A and D in spaghetti model has to be repeated. So due to that, the lot of redundancy increases and the file size and everything goes on. So there was slight modification of the spaghetti model, which is called a time models, where 2 separate files is being created instead of having a single file. In first file, you have only the point locations. And in the single file, you just take different features and you just keep a pointer to the first file where that like this feature is consist of how many points are there that is being stored. So this is basically also called an vertex dictionary based method. And if you want to have a topologies, then so you also need to have a kind of relationship that which is on the left and right side. We'll be seeing more in detail on topology at later stage. So any questions till now? Any question? Okay, so I'll move on. So then people have started creating more organized data structures, especially in case of commercial software like ArcGIS, where they created a polyword node data structure, which was being created in such a way that during the digitization process itself, your topology is being built. So that was a kind of start and end node and everything point was being stored at the beginning only. So with that, topological relationship was already built in data structure. So this was a kind of important development where a lot of analysis could be carried out. Let's say I wanted to find out what are the features on the left side of C, line C. So we can easily do those kind of query. But disadvantages of that has arise or was being observed quite quickly, that person who is creating these features has to be aware of the internal data structure of your GIS models, and they need to make sure that they do or digitize or create their data set with considering that. If they are not doing it, then at the end of the digitization processes, they have to do some kind of cleaning that has to be carried out. So it was a kind of cumbersome data structure which was difficult to maintain. But there are also few modification had happened at later stage, especially on the geo databases on OC. We'll see those examples. So those were basically the kind of vector data set. In the raster data set, you well-define a kind of grid structures where you say that this is my origin, and the origin standard starting and ending point, and the reference point is being provided over here at the origin. And then you say that each of these grids are located at specific distances or a specific pixel size. So with that, with the reference of these coordinate, if this, let's say for example, this is a point which is located at 8,4. So if I want to find out the location of this point, so what I have to do is I have to do a traversal of 8 rows, so 8 into the pixel size, and column 4 into pixel size. So that will get added to the lat long or xy coordinate values of the origin, so we can easily identify and locate. So in this case, what is happening is that the referential point or the coordinate system or the reference point latitude and longitude is being stored, but not for individual locations. So individual location position is being computed during runtime based on the pixel location. So we know the pixel location, especially we are having a tuple like this, where 8 and row and column can be provided, and we know what's the pixel size. So based on that, we can easily define by just simply doing a small mathematical operation. So in this case, georeferencing point is only available at the origin. All the other points are not having georeferences point. Where in case of vector data, you have to store the reference location point of each of the individual points. That's what we have to keep in mind. So this becomes an important aspect when you are dealing with multi-resolution data sets. So let's say if you are doing a climatic data sets or a meteorological data set which comes in 0.25 degree and 0.5 degree, and then you will be having a classification of Landsat imagery which comes at 25 meters. So the alignment of these two coordinate, whenever you want to do any kind of operation between meteorological data and actual Landsat data, then in that case you have to build some kind of coherence between those coordinate systems, and that is possible only when you know what are the pitfall of the coordinate systems and positions and how much pixel you will be losing, what may be the latitude and longitude impact. If you just click with the same boundaries of the meteorological data and as well as the Landsat data, you'll see that those raster data sets are not appropriately matching. So there will be some kind of mismatch which may cause during the modeling process. So alignment of these raster grid coordinate system is must for doing or processing the data sets. The impact of these two data sets, the same feature, and like in the vector data, you're having a very smooth representations, where in case of raster data, now this whole grid or pixel is being considered to be filled with specific features, and the impact of that is now this is being considered as the shape of this will get a kind of staggered effect. This we have to keep in mind. So in the larger cases, sometimes what may happen is that if you're having a polygon-based or vector-based data and you want to do some kind of raster-based model software where you are using it, so it will require you to do a rasterization process. So it means like these polygons needs to be converted into a raster file format. And during these conversions, there are a lot of like fallouts. Like in some cases, you may get a discontinuity. Like over here, this river is continuous, but as soon as the rasterization is being done, so there was not enough width of these areas for the which could be covered in a pixel, and we see that there's a discontinuity arising out of it. So in some cases, there may be a loss of area as well. Some feature may get lost. For example, if you see that there are quite a significant size of these polygons, which just reduces to a small pixels and so on. So such kind of like basically fallout, which is possible when you do a data conversion from vector to raster. So this is also an example where a simple smooth linear feature and how it looks like in a raster images. But you have to do conversion. So during in some cases, like some software will allow to do modeling only at the raster dataset. So you have to do conversion. So while doing a conversion, you have to make sure that you choose an appropriate pixel size so that the discontinuity is not being observed. So it means like you should know in your whole data set what is the minimum width of any linear feature or polygon feature is there, and based on that the pixel resolution should be selected. In case of raster datasets, you need to have some kind of because in the raster dataset you are storing all the information from, especially these are the attribute information. So it means on the grid values, whatever information is there for each of those values is getting stored. So people saw that there were a lot of redundant information. Like in this case, first row is storing no data values. So it means like there's a same value is getting repeated. So due to that, there are a lot of compression techniques is being applied. Like one is called run length encoding, which simply says that in each row, what is the repetition of particular values. Like in the first row, it's a repetition of 0 8 times. In the second row, you have 0 repeated 4 times. Then this red is actually having an attribute value of 1. So 1 is repeated 3 times. Then again 0 is repeated 1 time. So the impact of this is that for this a small area where if you want to store information, so you have to store for each of these grid values. So there are 84, 8 into 8, 64 different grids are there. So if you, let's say if you are storing a byte for that, so accordingly there will be an 84 byte information has to be stored for these cases if you don't use any compression technique. But the same after doing an application of simple run length encoding, so this reduces to around approximately 20 pairs. So around the 40 byte information is sufficient instead of storing a 64 byte information in this case. So this is very a simple way of showing the efficiency or of applying the compression algorithm on a data set. So this used to help in reducing the data sizes, and that was quite important, especially whenever you are having a scarcity of your spaces. So this is one way of run length encoding. Similarly, we are having an chain length encoding, which just goes, which starts from a locations and then simply starting locations, it is being provided, and then you say how much you need to traverse in one direction and so on. So basically, it gives you the outer boundaries, and that's we call it a chain length encoding. The block encoding is basically the largest block is being found out, like what is the largest block or size. Like in this case, we are having a block size of 9. So this is the biggest block. Then we are having a 2 by 2, 2 by 2, 2 blocks are there. So after completing this, we are still left with block size of 4. So these 4s are there, which are being left. So total one big block of 9 block size, 2 small block of 4 size, and 4 block of 1 size. So that's how we can store it. So this is basically a block coding. And today is most widely So applications or basically the raster compression is being applied based on the quadtree encoding. So quadtree encoding, what it does is it divides the area into 4 by 4 sections till it gets the same kind of information. So like this is a 16 by 16 and like basically 8 by 8 blocks. So it is getting divided into 4 sub blocks. So first block is we reach to a first block where all the informations are seen or same, so that is being stored and there is no further division is being done. But in case of second block, we are seeing that there are a lot of heterogeneity is there. So this is broken down into another 4 blocks. So we reach 3 blocks to be of uniform size, and 1 block is again having some kind of heterogeneity. So that's what we do. So 3 blocks is being given, and there's no further division is being done. But on the 4th block, we are doing a subdivision. So this is the quadtree encoding is being applied, which lets you store the information in the compressed format. So if you see, there are 2 different data structure, vector and rasters, and there are advantages and disadvantages of it, and the differences majorly can be brought in how those information are getting stored. So generally all the geographical phenomenon which is discrete in nature, the object-based model are being stored in vector format, where the field-based information is stored in the raster format. The point in the vector can be a fraction where in case of raster, the fraction is not allowed because each of the object is considered to be occupying the whole grid, not a part of the grid. So that's the basic differences, and due to that we get all those Zager effect or the staircase effect. Most of the time this is going to take a less space because the most of the vector data set will have only a few data points, where in case of raster data set you are having all the grid, so all the location grid points are stored. So accordingly you may be having a very large space requirement for your data sets. Basic objects are there in vector is point line polygons. It means like geometrical based operations will be performed, where in case of raster analysis you have basic object or cell as a grid. So once, since all the raster operations are being performed on a grid by grid basis, so grid loses its relevance. Only simple algebraic based analysis can be carried on. And as I told earlier, that in the vector, each of the point will be georeference, where in case of raster, only the origin of the point is being referenced, and all the cell location is being computed based on the locations and corresponding pixel size. And that's why the pixel size is an important factor whenever you are deciding on creating any raster dataset, along with the projection systems. So there are multiple formats most widely used like shapefile, KML, KMG, or different OSM formats and other things. Those are a vector file. And in the case of raster file, you have GeoTIFF, IMG, or SDF, network file, or the NC file. Those are basically the raster-based data formats. For 3D, we store one of the simplistic model is called triangulated models. That is the triangulated irregular network model. So in this case, you have X, Y, and corresponding Z location as well. So that's how you create individual nodes. So there are total 7 nodes are there. So accordingly, 7 nodes location X, Y, and corresponding Z information is being stored. And then a triangulated algorithm is being executed, which makes sure that there's no intersection of a circle which passes through any of those points, and like any of these 3 points. And then the radius of that circle is the minimum possible between 3 closest points. So there are 2 different constraints being applied, resulting in a kind of multiple triangulated surfaces. And that's how the triangulated network is being built. So you will see the KMG file or different gaming or CAD systems, the triangulated based irregular network is being used for storing the surfaces. Okay, so that was the kind of brief introduction of different data structure, especially at the logical levels, which is being used in GIS. There are a few important aspects also in case of GIS that is called the kind of spatial relationship. So a spatial relationship can be broadly classified into eight of these categories, which basically say that if one object is not connected to second objects, that is disjoint, or there is only a sharing of a node. So it means like there may be a sharing of a node. So then we say that these two features are actually meeting to each other. If one feature is completely covering the other features, so it means like we call it as an equal. If say that one feature is inside of the other features, that's the containment relationship. Then we are having a covered by relationship. So it's a super and basically a way to say that what are the different objects which is present inside, that's a covered by. Similarly, we're having a containment which is completely inside, not sharing any edges, but it is inside. Then cover, basically it may share a kind of some portion of the boundaries, but all the other parts will be inside the another object. So these are the few spatial relationship which is there. And with these spatial relationship, based on these spatial relationship, you're having a multiple spatial analysis which can be carried out. So this all spatial relationship also builds a kind of specific relationship. Those are called the topological relationship. So topological relationship basically says that if you do any kind of transformations of the different objects, so this is just a simple piece of paper. So whatever the paper you do or some kind of folding, converting these 2D objects into the 3D objects, but whichever polygon or the point which is on the left and right will always remain on the left and right side. So it is not going to do or make its changes. So that's what the most of the origami which is being built, this spatial relationship is always being maintained. And this basically says a kind of transformation invariant properties where locations or the spatial location of the point with respect to each other. The property of the location doesn't mean that the distances, but rather in terms of the left, right, top, bottom, south, west, east, such kind of locations, the properties are not getting distorted. So that's how the topological relationship is being maintained. And all the software basically nowadays allows you to maintain this topology. So generally topology will have a kind of start and end node as we have seen in the R file. And it will also store that which one is on the left and right side. So this is just a line. So on the line, let's say on 3, you're having a left side. If you take the starting and ending point, so on the left and left of that is basically the B, polygon B, and on the right side is the polygon C. So that's being stored. So this topology becomes an important case. Let's say, for example, if you're having a road, and on the left side of the road is a kind of river, so you cannot do any expansion. But on the right hand of the side, you're having some kind of space available to you where you can propose that there is a possible of increasing the width of the road. So in that case, you can create a kind of buffer analysis on a specific location that is only on the right side of the road, because on the left side you are not having any space available. So that kind of query is only possible if your system is having a topological property built. So this is just an example of the same topology also is being built in case of tin models, where also we say that on a specific triangle which is on the left and right, that is being stored. So for the edges we store. Similarly, also we say that each of those nodes belongs to which part. So in the triangulated irregular network or tin model, is also having some kind of topology built. Now, all those property, whatever we talked about, were related to geometrical property or objects. But now what we'll see that there is also an attribute-based information. So most of the recent database systems, what happens is now they are able to store the models in a relational models or object relational models, which can now be also stored which can also store nowadays the geometrical properties or geometrical objects. So since we have seen that how the geometry is being created, we will be having a kind of tabular structure where points are being defined. The relationship between point is going to give you a polygon or a line. So as a concrete tabular structure can be created that can easily be modeled or transferred into relational models. So that's how the different databases like PostGIS or the is going to have a spatial extension of Postgres. Similarly, in case of spatial data light, which is the SQLite extension, which is again storing its relational models. So they are storing it and as well as providing you few geometrical operations stored as an object store that can be used for doing the spatial analysis. The big data cases, you're having a files which is being stored. It's a flat file format that's being stored. So in case of big data cases, still the database technology is not matured enough to store a very large data sets. The flat file is being preferred, but in most of the traditional GIS analysis, you'll be having or you'll be able to store the data set in nowadays any relational databases. So generally in relational databases, what happens is the geometry is being stored at one locations, and then you link it with that geometry with some kind of attribute information you link it. So that linking is being built in, and this is called a relationship between those two. And these relational tables is being used for doing query-based analysis, which whenever you want to do, like you want to do a filtering of specific polygons with the name or some condition. So those these attributes plays an important role, and based on that, we can do a filtering. So this is just an example of how the whatever data structure we had. So the personal geodatabases is very widely used in closed source or ArcGIS softwares. So we'll be having a personal geodatabases. Inside that, we'll be having a few feature data sets, and those feature data set will be actually sharing the same kind of projection and coordinate systems, but there will be a multiple geometrical attributes. So those feature data set will have different features sharing the geometrical locations, but the common referencing and projection system will be stored in a feature data sets. The personal geodatabases can also store your raster data set. It can also store your network data set, which becomes an important requirement whenever you want to find out continuity or carry out any kind of network analysis. For example, if I want to find out the shortest path between any place on the road to a hospital. So in this case, there are different hospitals and there are multiple different kind of roads. All of these points gets combined together and you get a simple network structure which contains all the points which is present in hospital road with a minimal distance connection. So that's what the multimodal network is being created. So your geodatabase can store network structures. It can also store different features. So like ArcInfo data sets, tick points, polygon, things can be stored. It can also store the shape files. So like you're having multiple shape files that can also be stored, and as well as few attribute informations like the DBF file, which can be combined together with some other spatial data sets to give a complete picture. So So the modern personal geodatabase are able to store the information. So this is basically a logical view. And if you see on the background how the dataset is being stored in your file system or on your hard disk, will look like something like this way. So one shapefile which you're seeing it over here is a single file, is actually going to have another 6 files, supporting file, which is required to give the complete definition of the shapefiles. So most of the time, whenever people use shapefile as an entry point or creating a digitization, so most of the time what happens is that people will be just sending the SHP file. So PRJ or DBF file will not be given. So accordingly, the projection information will be lost. So as to the rookie GIS analyst makes those mistakes at the beginning, but this has to be kept in mind. So if somebody tells you to send a shape files, you have to send all these shape files combined together. At least 4 files is needed. Like you'll be having an SHP, PRJ, SHX, and SBN file has to be there. So these has to be sent to another user. So this is just an example of the same data sets. I think I'll just, I have already told that in your feature data objects, you'll be having a spatial references, those objects class and subclasses, then their corresponding relationship. All those things is being stored in a simple geodatabases. So earlier what used to happen is that all these data sets and databases or the organization of these data were quite different. So people had come up with a kind of standardization process, and that standardization is being provided by Open Geospatial Consortium or the OGC. So what they have done is they have created a high-level logical and the conceptual and logical data structures. So which says that how the geometry has to be defined, which not only stores or provide the information of, which is inclusive of existing data which is present in the GIS domain, but it has also made sure that in the future, like surfaces or the 3D objects, how it can be represented, they have also defined a set of rules, and that's how the standardization has now reached. And due to that, there are a lot of now interoperability between the software or the data format is possible. So this is just an example of geometrical objects, how it's being seen. So over there, point, line, polygons, point and curve is again another data set. Under that, you're having a line and surface is a polygon. Then there's a new data structure which is called a geometrical collection is also being considered, which stores the multi-point geometry. So this is specifically becomes an important aspect when you want to say, let's say, you want to define a department. So a department may have multiple buildings. So all those buildings combined together. So it means like a set of polygons combined together will share an attribute called some department name. So that's how it's in those cases, the geometrical collection plays an important role, and we define the basically the geometrical class. This is basically an extension of geometrical class, so which has a way to store points. So if somebody is claiming that its data is OGC compliant, then it should be able to define and provide details of point, line, string, and so on. So these becomes an important aspect. Let's say if somebody is providing a OGC compliant GeoJSON format, and you want to find out details of a specific structure, so you can look for that. Is it a line or is it a line string? And you can do a lookup into the tables, and easily you can find out the details. So those are the important data structure or the component which you are expected to find it in OGC compliant feature models. So the geometrical collection examples, like you have a set of data points which may be of similar features, like points or a polygon or lines. So these two, as a collection of multiple points or multiple lines, can be created as a part of geometrical collections, or it may also store an heterogeneous data. So it means it can store point and line both, point line and polygon. So all these things can be collectively stored in geometrical collection, which was not possible earlier in the cases. So on the web, we see that the GeoJSON format is widely used. So this is just apart from those standard shape files and TIFF files, the details you can get it on easily net. But on the GeoJSON is another format which is being used for transferring your data set from one system to the another systems. So this is basically an OGC compliant data sets, and it's basically a textual based data structure where object and sub-object hierarchy is being created as per the basically the OGC compliant cases. So over here on the top, you'll be having a feature collection. So inside the feature collection, you'll be having a lot of features. In the features, you'll be having a set of geometrical objects and few properties of these objects, like these features can have a name or properties, those can be stored. And then you're having geometrical objects. Then these geometrical objects can be a point line polygon, or it can be a collection of point line polygons, or it can be some other geometrical properties like point line polygons separately. So point line polygon, a set of point line polygon called multi-point line polygon, multi-polygon, and so on. Or you may be having a geometrical collection where heterogeneous data sets can be stored. So this is simple GeoJSON format. You can have a look on the net, and you can have a look of the data set which is in coherent with the diagram shown here. In the open source world now, especially in the QGIS, there's a new format called GeoPackage format is being introduced. And this GeoPackage format is a single file format which stores collections, curves, surfaces, point line, polygons. So all those things are the different geometrical properties which is defined in OGC are being stored in case of GeoPackages. So GeoPackages are any software which support the JPKG format are expected to provide a minimum support for the core. So those are the yellow lines, that is point, line, polygon, strings. These are the core which should be supported. Then only we will say that GeoPackage is supporting the core. But apart from that, it is also supposed to support the extension of the different geometrical objects. So these are the new upcoming formats which is being used in QGIS and cases. Now coming to the uses of all those data structures. So you have stored your data, you have organized your data considering the appropriate way. Then we will look for some kind of analysis. So generally in GIS, we look for a different kind of analysis, like especially the location-based analysis. What is at specific locations? What are the different conditions where filter-based approach is being taken? So like which city is having a maximum population density. So you're having a set of cities present in your data set and you want to do a simply query. So those are conditional query. Then we also look for a kind of sometime trend. So it means that a temporal component gets added, which makes sure that how the things is changing with the time. And these temporal changes, if we are finding out any kind of specific patterns, so either those patterns may be on spatial domain or it can be a temporal domain. So those things can be considered as a part of patterns. And then finally, when we are done with these basic understanding of doing a geometrical operations and then trying to do an introspection of any specific process, then we'll try to do some kind of modeling approach. These modeling approaches basically whatever patterns or systems which you have derived, then it looks for what is going to happen or what are the different parameters. So those are basically an extension of GIS-based analysis. So any GIS-based analysis can be categorized in any one of these 5 categories. So let's take an example of cases where I want to find out the nearest school to my home. So it is like, that's what my question is there, or you may be having an just to give some kind of information like finding those are called a suitability analysis, where we need to have an multiple conditions. So this is just a single condition where I want to find out the nearest school. But in some cases, if I want to combine multiple requirements, then in those cases it's called suitability analysis. So like choosing where to locate a new refinery. So if you want to set up a new refinery or college or school, then you have to look for a lot of things, like where the catchment of the new students are possible. Is the school is any vacant place is available near to the road or at an appropriate distance from the road? What is the minimum size of those plots? So there are multiple conditions are being put in, and using those conditions only we can carry out some kind of suitability analysis. And then, as I was telling that on the higher up, you build a model, so you look for a kind of set of input-output variables and their associations, and based on that, you create a statistical or system dynamics based or differential equation based models. See, so these are the different geospatial analysis which we need to carry out based on our user requirement, and this can be converted into, so all these requirements can be brought down into different methods or the tools which is available in your GIS software. Like the first one will easily, basically can easily map to a simple spatial query or a single layer query. Sometimes you'll be having a multi-layer operations, like in this case, where the road network distances, the existing refinery locations, then the people where they are living. So that's another layer which is present. So if you want to find out the suitability analysis, you have to carry out a multi-layer operations. And then different kind of interpolations or the finding out shortest distance between the point and so on. So those are actually a part of surface and network analysis. And then modeling or the point pattern, this is basically modeling the process itself. So over here we are finding out the data set, but in this case, we look for a spatial processes. So is the process is a Poisson process or the random or a clustered process or not? Those kind of things can be carried out in geospatial analysis. So this slide just tries to give you kind of indexes of different GIS analysis tool which is available in vector and raster domain. So that can be grouped into either an overlay operations or the proximity or analysis, network analysis and pattern analysis based approach. So this is basically a vector-based systems, which will again have an like overlay. Under the overlay category, you'll be having union, intersection. So what are these? Few of those examples we'll see in the coming slide. Similarly, you'll be having in the raster cases a simple map algebra operations, which is equivalent to a map overlay in vector, but only difference is that this happens on the grid by grid basis, where in case of vector, this is being done on the basis of geometrical computations is being carried out, where the map algebra, you simply perform an arithmetic once the grid is properly aligned. Then the other terrain analysis or hydrological analysis and reclassification. So these are the few additional analysis tools which is available. So for example, let's say I want to find out all those locations where, let's say, land use it, or maybe I'm having a few conditions that the land use of particular type. Like I want to find out only the non-forest areas. So what we can do is we can simply do a selections where the forest can be selected and other can be filtered. So this is what you get it the output. Similarly, you can have the locations where you say only the places where area is the forest area is there and steep is the slope is according to my requirement. So combination of these two is going to give you an output, and these output is being generated by carrying out a simple algebraic operation between these two layers. So you can say the layer, based on layer, you can take multiple layers, and you can perform a simple AND operations to generate an raster layer analysis. In the vector layer overlay operations, two different maps or multi-layer datasets are overlaid one on the top of the others. Then you get multiple regions, and all these regions inherit the attribute of both the maps. And after that, based on the kind of operations, like if you're using a union, then all these new locations are being created and the attribute of these two will be attached. But if you're looking for a clipping, the information or the operator of second maps, all the places where it is present, those will get removed, and on the map, one map, the other places will remain, and corresponding attribute of A will be stored. So there are multiple operations which can be performed. But in any kind of vector analysis, you have two maps, and these two maps are actually overlaid on the top of the others, and dividing the whole region into multiple sections, and the attribute gets transferred from one location to the both the maps get transferred to a new table. So this attribute information is being provided, and then after that the simplification happens. So another example of spatial analysis is the proximity analysis. So you want to find out the locations around few points at a distance, or you may want to find out a range of distances along a road. For example, you want to find out a buffer zone of 100, 200 or more than 200 cases. That's how the neighborhood functions can be created, where it will lead to a kind of proximity buffer zone. And within proximity buffer zone, you can do a counting. For example, you're having a school location here, and you want to find out how many households are there around these schools. So first you create this buffer, and then within this buffer polygon zone, you start counting the number of houses. So that's the counting cases can be done. So this is just an example of finding out a suitable site for a schools where you're having a multiple like data set like building, road, and other vector data sets, and then we simply use GIS tools like distance or the neighborhood areas. That's basically a buffer zone. Then the land use classifications, then polygon classifications, and giving the conditions, we can create a set of suitable locations that can be created to carry out a simple spatial analysis. Then apart from those, based on the input data set, sometimes the spatial analysis can be used for filling the data set. So like you're having a few locations where measurement is being provided, but you want to do an estimation for all the location where measurement is not available. So it's a kind of interpolation approach. So if you want to carry out interpolations, there are a few methods, spatial methods, the kriging and all, which can be used for doing some kind of estimations. Or sometimes we may be interested to find out two separate spatial patterns. In these cases, it's basically showing that two different industries like software and telecom, and they are co-located. So it means like all the locations of the business or the companies which was earlier in a telecom sector. So just beside that, you are having a lot of software companies has arise. So this is basically a centroid-based analysis. So this basically tells that these two different phenomena, the location of the telecom industry and location of the software industries, those are actually interlinked. So that's basically a kind of co-location process can be identified. Or you may be also interested in finding out the kind of the processes, like you're having a set of data points, and these data points, does it show a random or it's a kind of some kind of clustering? If you think that it's a clustering, then how much clustering is there? Or if it is a random, is it really a random? So that can be modeled with a spatial pattern analysis, and that's what we use multiple spatial distribution process models, and that's basically takes the hypothesis of taking clustering, non-clustering, or something like that. Based on that, simulation is being carried out, and you do a comparison of redistribution of those locations, and you just do a comparison that if the process would have been, let's say, Poisson's process, the output is, so based on that you create few random points and you do a comparison of the output and final the process models and the actual data sets. And if it is matching, you accept that particular process, maybe the cases. This is another example of why we do spatial analysis. So this is a John Snow famous example where a lot of malaria, basically the cholera death had been observed. So it has been boils down that after doing a simple mapping, it boils down to that all these cholera are linked to a kind of specific, water sources, and that's how the theory that the cholera is a waterborne disease has been arrived. So this is basically you do a kind of descriptive modeling you carry out. Similarly, the future allocation and other things you can do a predictive modeling can be carried out. So there are also a few new applications coming in 3D GIS, which is a combination of 3D visualizations, animation, virtual reality and augmented reality and mixed GIS. This is just an example where you can create basic 3D data models or 3D data sets, and based on that you can combine, look for a kind of change detections or ecological modeling you can carry out, like how much energy is being consumed in a specific zone, what should be the power distributions, or you can also look for a specific location, like what are the different potential of each of those buildings based on their arrangement and the way they are being oriented. And so on that can we create a kind of energy efficient location or zonation maps which can be used for promoting it. Similarly, it can also be used for disaster and flood management. So all those 3D GIS based base layer is there, and based on that, multiple analysis can be carried out. So like few of those analysis, which is in a simplistic way, is that you do an attribute based query, or you do data classifications, like you want to find out based on the distribution of the income group, you do a categorizations, and it will give you kind of distribution of resources in a particular city. You can also look for any specific conditions where you can provide, like based on a specific height, you can do a classifications. And there are also a modeling based approach which can be brought in for the temporal animations. So there are other 3D analysis techniques like 3D buffer analysis technique, so which is a kind of showing the impact of if any explosion happens around that, which all building will get affected. And if you combine with the attribute of different buildings, then it will say that how the building is going to have resistance. Then the other geometrical properties like surface area computations, the distances or the length of the building computations and all. Those are also the 3D spatial the query which can be done. Surface area becomes an important. For example, let's say if there is a decision is being taken that we have to paint the whole city in a pink color. So there has to be some kind of estimation of the cost. So if you know the proper height building information, so approximate cost for that actions can be created. So these are the 3D analysis. Then apart from that, we are having a view set analysis. This is basically important for security or the camera placements, which gives 3D space, 2D or on the ground, what are the area which is visible that can be seen. So the shadow analysis or the terrain analysis, basically trying to find out the shadow region areas. Or we can also do on a particular day, what is the total solar energy which is available in a building, because nowadays we are having high-rise buildings, so there is a shadow is going to fall on another building, so all the energy may not be available for the whole day. So that's the 3D analysis which we can carry it out. There are also an extension of 3D GIS which is being shown, like we can find out what is the impact of any specific disaster if it happens, then which all area will get inundated, and accordingly we can do a categorization, and or the categorizations can be done for different building, and we can create an zone areas and other things can be done. We can also create within a building which is particular area or is safe or not. That kind of large scale simulation can also be carried out. So this is the new technologies which is coming in, that is called a VR based technologies, and with this we are having an enhanced location based service capabilities. Like in this example you see that on your mobile phone itself, this is going to pull you and provide you information in the real time and giving you map detail or navigation detail in the real time. So based on that, you can view it. And there are also perception 3D analysis with the help of like you're having an AR glasses, so that can be used for perceiving the 3D terrain. There are also panoramic on location view. So on the move, you can find out the location and other things can be carried out. In fact, the taggings can also be done. So this is just an example of tourist-based informations, other detailed information which we can provide, which can be provided. So these are basically a few enhanced spatial analysis techniques, which is not only present in 2D world, but also in 3D GIS dataset, it is also present. So with this, actually, I finished my lecture. So if you have any specific questions, so I'm ready to take those.
Anyone have any question? I request from the audience.